My name is Sung Kim. I'm going to introduce a paper, Stitching Sub-Trajectories with Conditional Diffusion Model for Goal-Conditioned Offline RL. This work is conducted by Sung Kim, Yunsun Choi, Daiki Matsunaga, and Kyung Kim from Kim Daechul Graduate School of AI, KAIST. In the background, I will explain what goal-conditioned offline RL is, and then describe detailed problem settings. Next, introduce some related works step by step. First, diffusion model, which is our tool for learning policy. Second, hindsight experience replay, which is popular technique for solving GCRL. And finally, the first attempt to solve our problem with diffusion policy. And our method, experimental results. Finally, conclusion. Let's start from reinforcement learning. RL is decision-making process maximizing expected return. Elements of RL are agent, environment, state, action, and reward. Traditional RL, so-called online RL, does not require training dataset. The agent collects dataset by interacting with the environment. This process is called trial and error or explore and exploitation. However, online interaction with the environment requires a high cost and risk. For example, training autonomous driving agent with online RL can lead to extensive loss. Thus, offline RL came out in purpose of achieving high performance entirely without interaction with environment during training time. The main goal of offline RL is to achieve better policy than simple behavior cloning of the offline dataset, which is called data collection policy. Due to its cost efficiency, offline RL is now the mainstream in RL domain. And goal-conditioned RL is an RL situation involving those goals. The characteristic of this RL is that we have to learn policy that depends on given goal, which means multitask RL. Also, GCRL usually has problem of sparse rewards. Sparse rewards problem results from the reward function of GCRL, which usually indicates whether current state is goal state or not. This simple reward setting is very practical because in many cases, reward function is difficult to define. However, learning optimal policy becomes much more difficult under this sparse rewards problem, especially in offline setting where interaction with environment is restricted. Such a lack of reward signal makes problem trickier because approximation of value function becomes more inaccurate. To define GCRF problem setting, I will explain goal-augmented MDP. S is set of states, A is set of actions, P is transition probability, R is the reward function, G is set of goals, mu0 is the initial state probability, and gamma is discount factor. The difference from plain MDP is the existence of G, and we assume G equals S for simplicity. Also, reward function R here is binary function indicating goal is achieved or not. Important thing in GCRL, policy depends on not only state but also goal. And more details of our problem setting. Our offline data set is composed of sub-trajectories, which are split into 8 horizons. We define sub-trajectory xt to t plus h like this, where h is a specified fixed horizon. Additionally, we define sub-trajectory reward given sub-trajectory x and goal g like this. Also, we assume each trajectory terminates when it achieves its goal, receiving reward 1. Then the action value can be written like this. For a given state action pair S, A, the probability for the policy pi to achieve goal G. That's all about background. Let's move on to related work. It is divided into 3 sections. First, diffusion model. Diffusion model aims to learn the reverse process of certain stochastic process. Here, the stochastic process is called the Ford process, which progressively corrupts given distribution. Once we learn the reverse process of this Ford process, we can generate samples following the distribution of interest fixed from fixed shape of Gaussian noise. Note that the first script denotes diffusion time step I from ranging from 0 to large N. X large N is Gaussian noise and X0 is trajectory for our case. Please don't be confused by subscript, which denotes trajectory times step t. Second, hindsight experience relabeling is a very famous and popular technique for GCRL, either online or offline RL. The idea is simple. Here, original goal is red point and achieved state is circled in green. The trajectory, this trajectory, is failed trajectory, so there is no reward signal. However, if the goal was here, this trajectory is valuable as well. By relabeling the original goal with achieved state, her enables the agent to learn useful skills even from failed trajectories. Combining with her technique, existing RL algorithms made significant improvement of performance in GCRL setting. But this relabeling technique involves hindsight bias due to the gap between distribution of original goal and distribution of relabeled goal. So there are also some approaches to reduce hindsight bias. Third, with diffusion, planning with diffusion is the first diffusion-based policy to solve our problem. Our research is motivated from diffuser, and it is main baseline. To solve GCRL tasks, they simply employs her and then imitate the data distribution with diffusion model. It is kind of trajectory-wise behavior cloning with diffusion model. Even though the idea is very simple, diffusion showed state-of-the-art performance in GCRL task. But the problem here is diffusion aims to generate full trajectory with fixed length. It is due to property of diffusion model, which requires fixed shape of the dataset. But it is unrealistic to assume that the length of trajectory is known a priori and even independent on distance between current state and the goal. Our research starts from problems of diffusion policies in GCRL domain. So our goal is to solve offline GCRL problem with diffusion-based policy. For existing methods, there are 2 main challenges. First, stitching is tricky. And second, problem of guidance when conditioning diffusion models. I will explain in detail in the next slide. The goal of offline RL is to obtain better policy than the data collection policy. Therefore, it is important for offline RL algorithms to learn how to make optimal trajectory by stitching suboptimal trajectories. This is called stitching ability. Moreover, in GCRL, the sparse nature of reward functions makes it challenging for traditional RL methods to accurately capture the valuable portions of the dataset and integrate them appropriately. Our goal here is to train a diffusion model that is able to generate both successful and failed trajectories. For example, assume that the distribution of original goal is near red point, and we have such two types of data set, failed and successful. The point is our algorithm should be able to generate such failed trajectories as well that would arrive at the goal in the future when stitched with other sub-trajectories. Here, each arrow is sub-trajectory. Therefore, we use action value as condition for diffusion model, where the action value is estimated with a novel relabeling technique differentiated from her. While diffuser, which relies on her, aims to generate only successful trajectory, our relabeling method allows failed cases. This is because our purpose is generating sub-trajectories and stitching them, so every sub-trajectory does not need to be successful. It should be able to generate failed sub-trajectories on the way of goal. So this condition is for successful case and otherwise is failed case. As a result, we use TD target of below. We propose to train action value with our relabeling technique and then use it as a condition of diffusion model to improve stitching ability. Second challenge comes from how can we condition the diffusion model, which is called guidance. In image domain, conditional diffusion model is studied a lot. For example, the guidance is classifier, which is a neural network as well. And the task is to generate image of cat, for example. This is called classifier-guided diffusion. In RL case, action value can be viewed as kind of classifier. However, it has been pointed out that training separate guidance makes additional error. So Ho et al. 2022 proposed classifier-free guidance. Subsequently, classifier-free diffusion model was adopted to solve our problem following after diffuser. But classifier-free diffusion did not work well in RL domain, generating such unrealistic trajectories, because the generated trajectory should satisfy the constraints of MDP, such as staying within the state space and following the transition probability of the MDP. So naively applying conditional diffusion model of image domain is not a good idea. Thus, we propose a novel architecture called condition prompted UNet. We replaced convolutional blocks of diffuser with transformer blocks, treating the condition as one-off tokens. The transformed blocks provide the capacity to capture complex patterns of real-world sequential data. This architecture is designed to address the challenges of trajectory generation in RL domains, ensuring compatibility with environment constraints. Furthermore, CPUNet does not require an additional guidance model and thus reduces overall approximation error. To sum up, we aim to generate sub-trajectories with conditional diffusion model and stitch them to form a full trajectory. First, we train action value with our relabeling method to improve stitching ability. Second, we train conditional diffusion model depending on the action value. During evaluation time, we take actions utilizing generated sub-trajectories. We use first case steps of the generated sub-trajectory as usual planning methods do. Therefore, we generate sub-trajectories every case step until the episode terminates. We conducted experiments in two distinct environments, Maze 2D and Fetch. Both of them are representative GCRL tasks. Maze 2D is navigation task where the goal is red point. There are various difficulty level, U-Maze, medium, large. This slide shows very interesting ablation results. As I pointed out, existing diffusion policies do not have stitching ability. Thus, they generate fixed horizon of trajectory regardless of the distance between current state and the goal. Here, diffuser and DD go around for 2056 steps, which is determined a priori. However, ours generate direct trajectory because we aim to generate small sub-trajectories and stitch them. In large domain, our baselines, diffuser and DD should search appropriate horizon 384, but we use constant horizon of 64. This is constitutive result of diffuser. It is normalized score with standard error. Maze 2D is task with fixed goal, and multi 2D is task with distinct goals for each episode. At the time, diffuser beat other RL algorithms with huge gap. And this is our report. Even though DD and HDMI made further improvement following after diffuser, they show lower performance than two variants of diffuser, which is conducted by ourselves, and it uses classifier guidance. Implementation details of diffuser HER and diffuser AM can be found in the paper. Finally, ours shows state-of-the-art performance with huge gap, beating all the baselines. Fetch is a robot manipulation task. There are 4 tasks: reach, push, pick in place, and slide. Except for reach, those domains have object to be moved, which makes the task more difficult. This is average success rate with standard error. The baselines are representative GCRL-specific algorithms. All of them involve relabeling methods to adapt to GCRL domain. Ours shows state-of-the-art performance as well. This is average discounted return with standard error. State-of-the-art performance in average. In conclusion, we used conditional diffusion model to solve offline GCRL problem. There were 2 challenges regarding stitching and guidance. First, we aimed to improve stitching ability. So we trained the conditional diffusion model that generates small sub-trajectories and stitches them. At that time, the condition is action value, which is estimated with novel relabeling method. It is beneficial since we don't need to predetermine sub-goal or terminal time step large T. Second, we presented novel conditioning mechanism without separate training of guidance. Those contributions made great improvement of performance in GCRL domain. Thank you for listening.